Moving on to section 2, Ohm's law and resistance. Ohm's law is one of the most important relationships in this chapter. It states that, for a conductor kept at a constant temperature, the current flowing through it is directly proportional to the potential difference across it. The constant of proportionality here is called resistance. So we get the simple equation, V equals R. But remember, Ohm's law is not a universal law. Only ohmic materials, mostly metals at constant temperature, obey it. Non-ohmic devices, like diodes, transistors, and gases, do not follow this simple linear relationship. Let's compare ohmic and non-ohmic conductors side by side. For ohmic conductors, the V-I graph is a straight line passing through the origin, and the slope of that line gives you the resistance. At higher temperatures, the slope becomes steeper, meaning resistance increases. Metallic wires at constant temperature are the classic example. Non-ohmic devices, on the other hand, give a curved, nonlinear V-I graph. Sometimes, the current even depends on the sign of the voltage, and in some cases, more than one voltage value can give the same current. Diodes, transistors, and thermionic valves fall into this category. Now let's formally define electrical resistance. Resistance is simply the opposition a conductor offers to the flow of current through it. Its SI unit is the ohm, which is 1 volt per ampere. In terms of dimensions, resistance is M1, L2, T-3, A-2. And resistance isn't just a fixed number, it depends on the conductor's length, its cross-sectional area, the material it's made of, and its temperature. Resistivity is like a material's fingerprint. While resistance depends on the shape and size of a conductor, resistivity, denoted by the Greek letter ρ, is a property that's intrinsic to the material itself, completely independent of its length or area. The relation is R equals ρ, L over A. If you rank materials by resistivity from lowest to highest, you get conductors, then semiconductors, then alloys, and finally insulators. Silver has the lowest resistivity of all, while fused quartz is among the highest. And resistivity increases with impurities, mechanical stress, and for metals, with rising temperature. Two closely related terms often confuse students: conductivity and conductance. Conductivity, sigma, is simply the reciprocal of resistivity. It tells you how well a material conducts electricity in general. Conductance, C, is the reciprocal of resistance. It tells you how easily current flows through one specific component. Its unit is Siemens, sometimes written as ohm inverse. Don't mix these two up in your exam. Here's a classic numerical concept. What happens when you stretch a wire? Since the volume of the wire stays constant, as the length increases, the cross-sectional area must decrease. This causes the resistance to increase quite dramatically. In fact, if the length becomes n times the original, the new resistance becomes n squared times the original resistance. In terms of radius, resistance varies as the inverse fourth power of the radius. This little trick shows up again and again in exam problems, so keep that n squared relation firmly in mind. Let's look at how temperature affects resistance. For metals, like silver and copper, resistance increases as temperature rises, so the temperature coefficient, alpha, is positive. But for insulators and semiconductors, it's the opposite. Resistance actually decreases as temperature rises, giving them a negative alpha. This temperature coefficient is defined as the fractional change in resistance per degree rise in temperature, and its unit is per Kelvin, or per degree Celsius. One more interesting point: magnetic fields increase the resistivity of most metals, except for iron, cobalt, and nickel. Every carbon resistor has colored bands painted on it that tell you its resistance value without needing a multimeter. The first band gives the first significant digit, the second band gives the second digit, and the third band tells you the multiplier, basically, how many zeros to add. Black stands for 0, brown for 1, red for 2, and so on, all the way up to white for 9. A handy memory trick many students use is, quote, BBROY of Great Britain has a very good wife, unquote, where each bold letter represents a color in order. Now let's move to section 3. Combining resistors. When resistors are connected in series, the same current flows through every single resistor, and the total resistance is simply the sum of all the individual resistances, which means the combined resistance is always bigger than the largest resistor in the circuit. Voltage divides between them in proportion to resistance. In a parallel combination, it's the opposite. The same voltage appears across every resistor, but the reciprocal of the total resistance equals the sum of the reciprocals of each resistance. This makes the combined resistance smaller than even the smallest resistor, and current divides inversely with resistance.